Recording in
All
progress.
right, hello folks. Welcome back to our conversation about Gibbs free energy. In this lecture video, we are going to go over how free energy can be determined and related to a system at equilibrium, which, as we know now in Chem 220, that a chemical reaction, quote unquote, stops when it reaches equilibrium, right? So we understand that a chemical reaction actually never really stops. It just maintains this state of equilibrium. So, what are the energetics behind that? And how can we use this to identify if a system at equilibrium is like spontaneously established or not? So, let's talk about free energy and equilibrium. In order to understand this idea about how energy is exchanged when a system is at equilibrium, let's go ahead and define thermodynamic reversibility. Because we talked about this when we went over the assumptions that we make in our conversations about thermodynamics. But let's give this its own set definition. So, thermodynamic reversibility is the idea that some infinitesimal change in the energy of the system, let's call it dE using our calculus, can be recovered fully by reversing that system by some small amount d. So, like a good example of this, I think, is if we're talking about perhaps a phase change, or we're looking at liquid going to solid, or something like water. Oh, let's do this different color. Let's do that. So, temperature, reaction progress. Okay. So here, this is the region where we are in a phase equilibrium between liquid and solid. And this kind of system can be considered to be thermodynamically reversible because for every amount of heat dq that I put into the system, which then causes some change this way to create more liquid, I could completely invert by taking the same amount of heat out of the system, dq, resulting in an equal and opposite change, remaking solid. So it's like I can supply the exact same amount of small amount of heat, like maybe enough to, let's say, freeze one molecule of water. And then I could then deprive that exact same molecule of the exact same amount of heat and then remake. So you're depriving, following my train of thought. Add heat, make it liquid, deprive heat, make it solid. Okay. So again, as long as I can do these little like micro changes to my system where I can pump energy in and then a very micro state have out and like kind of like move back and forth along this equilibrium, this is what it means to be thermodynamically reversible. So it's all talking about these like very small infinitesimal changes where we're able to like fully recover and conserve our energy. So if we think about this on like a macro scale where we're talking about like big changes, delta, this is where things like we understand do not become like a thermodynamically reversible system, right? Like if I think about reactants then to products, my reactant state compared to my product state is not one that could be considered reversible, because I'm not looking at an infinitesimal change in energy. I'm looking rather at something like the delta H, or the change in enthalpy of reaction, the heat of reaction, or the delta S, the change in entropy of reaction, right? Big changes, deltas, instead of little tiny changes, Ds. Now, if we're at equilibrium, then there is the idea that K, the equilibrium constant, can be altered and reformed. Well, okay, not K, but let's say if at equilibrium, the system or reaction or equilibrium can be altered such that the equilibrium changes in one way toward the reactant, and then that alteration can be undone going backwards. That's what it means to be at equilibrium. So, okay, maybe I'm not saying this clearly. It's not so much that at equilibrium the reaction is altered, but at state of at equilibrium has some change this way for every small change in the reverse. I think that's a better way to think about it. So for example, if we're thinking about like reactant A plus B in equilibrium to form C plus D, if I were to zoom in on this, like if I were to look at a molecular scale of what's going on in this system, I would find that I would have A and B and C and D, where at any point, if these come together to form these, that's the forward reaction, there's also some innate reversibility to this reaction where these can micro go back, right? Like I can have like a material formation of product that then undoes that formation on a very, very, very small scale to go back to reactant. Which means that like the amount of heat for the forward has to be equal to the heat of reaction of the reverse. Let me get the color coding right. Right, if I want to thermodynamically like undo the formation of products. So let's just call this delta H forward reaction. Then I want to deprive that system of the exact same amount of heat, which I can call negative delta H reverse reaction. And in fact, the fact that these are like the same value, just opposite signs, this is our first law. So we're assuming any like microstate change, not microstate, any like microscopic change in the formation of product can be then like undone at a microscopic scale to reform reactant. And that small amount of heat, DH, to be specific here with our language, some small amount of change in the enthalpy of reaction can be thermodynamically reversed in the reverse reaction. Now, why is this important for us to know or understand when we're talking about spontaneity and free energy? So if a system is at equilibrium, then the delta H of the system is 0. And let's do DH. And overall, the entropy of the universe, specifically its change, is also, let's say not universe, but let's say system and surroundings. So the change in the entropy of the system is also equal to 0. So like if I were to think about this in terms of my definition of delta G reaction, where we are presuming we're at standard state, this would be equal to 0. Sorry, delta reaction. There we go. Delta G reaction would have to be 0 because this would be dH cis minus TdS cis, and both of these things would knock out to 0. So what we see instead is that if a system at equilibrium is established at standard state conditions, we see that the change in standard free energy of the reaction is equal to negative R times T times the natural log of K. So delta G naught is equal to the standard state change in free energy. R is the gas constant. Since we're talking about energy, it better be expressed in terms of joules. So this is 8.314 joule per mole Kelvin. T is the temperature in Kelvin. And K is equal to the equilibrium constant. So we can imagine what would happen if something like K is less than 1. So let's see here. Let's do something like the natural log of 0.5. If K is less than 1, then the natural log of K is negative, which means that the delta G standard is equal to negative RT times a negative number, which would be positive, and delta G standard of reaction, if we were looking at an equilibrium constant that was greater than 1, would imply ln of K. So let's do something like ln of 100. That is indeed positive. And thus the delta G reaction standard would be equal to RT times a positive, which is negative, So if we are at standard state conditions, then when K is less than 1, the change in free energy is positive for that reaction, which would mean we are not spontaneous. And if K is greater than 1, then the sign of our change in free energy of reaction would be negative, which would make us spontaneous. So this is looking at, again, the standard state free energy of a system, or change in free energy of a system at equilibrium. So system is already established at some equilibrium with a K. We are trying to figure out, if we're at standard conditions, the change in the Gibbs free energy of that reaction once it has hit equilibrium. And we have an idea about whether that equilibrium state is spontaneously established or not based on the value of our equilibrium constant. Now let's think about this. Remember our standard state conditions, one of our assumptions from like the first day we talked about thermodynamics, is that we are looking at exactly standard temperature, standard pressure. We are also talking about 1 mole of pure solid, 1 mole of pure liquid. And if we're looking at a solution, the concentration of all solutions must be equal to 1.0 molar. So if you think about like every single reaction that we've looked at in Chem 220, especially these aqueous phase ones, we have very obviously not been at standard state conditions, right? Like we have not been looking at only reactions of 1 molar substances so that we have like, you know, these perfectly standard ways of expressing how our reaction's occurring and what's happening with the equilibrium it's establishing. So how do we correct for like the real world? If this tells us the standard change in Gibbs free energy for a system at equilibrium, then let's look at non-standard conditions, meaning how does Gibbs free energy change? That's too big. When we are no longer presuming standard conditions, because this is more likely what we're going to be doing when we actually go to perform an experiment. So in our next video, we will talk about how we can correct for the Gibbs free energy term for a reaction occurring at non-standard conditions that does establish or will eventually establish some equilibrium. And then from there, we'll be able to derive the relationship between entropy, enthalpy, and the equilibrium constant through our understanding of how the Gibbs free energy of a system at equilibrium relates to the equilibrium constant, which will be helpful in our borax lab. So see you in our next video.